All right, let's talk about a piece of tech you use literally every single day, but probably almost never see. It's this silent, unmoving, and absolutely essential workhorse that makes our entire electrical world, well, work. Let's dive in. Seriously, just think about this for a second. You've got these massive power lines, right? Crisscrossing the country, carrying hundreds of thousands of volts. And yet you can take your tiny phone charger, which needs what, 5 volts, and plug it right into the wall without a second thought. How does that not just instantly vaporize it?
Well, it all comes down to this really interesting paradox. See, to send electricity over huge distances without losing a ton of energy, you need crazy high voltage. But to actually use that power safely in our homes, for our gadgets, you need really, really low voltage. So you've got these two totally different needs. We need a bridge between those two worlds.
And that bridge, the absolute hero that solves this whole voltage puzzle, is the transformer. This is the crucial link that makes our entire modern power grid possible.
So what exactly is this thing? A single-phase transformer is basically a device that moves electrical energy from one circuit to another. But here's the wild part. It does it with no direct electrical connection. The two circuits never physically touch. It just changes the voltage level, up or down, while keeping the frequency exactly the same.
If you break it down, it's pretty simple. You've got 3 main players. First, there's the perimeter winding. That's the indoor for the power. Then you've got the magnetic core, which is like the superhighway for the energy. And finally, the secondary winding. That's the outdoor. How these 3 work together? Well, that's where the real magic happens. So how does the energy make that leap? How does it jump the gap if nothing's touching? Let's take a look at the magic inside. Okay, it's not actually magic, of course, it's pure physics. The whole thing works because of a principle called electromagnetic induction, which was figured out by the brilliant Michael Faraday. It's all about this deep, fundamental connection between electricity and magnetism. Here's how it goes down in 4 simple steps. First, that alternating current, AC, flows into the primary coil. This creates a magnetic field in the core that's constantly changing, growing, and shrinking. Third, and this is the cool part, that fluctuating magnetic field travels through the core and starts interacting with the secondary coil. And finally, that interaction induces a brand new voltage in that second coil. Just like that, power is transferred and the wires never even had to touch. So, that explains how the power gets across. But what decides if the voltage goes up or if it goes down? Well, the secret isn't some complex magical spell. It's just math. And it's surprisingly simple. You see, it all comes down to the number of times the wire is wrapped around the core on each side. If you want to increase the voltage, you build a step-up transformer. You have fewer wire turns on the primary coil and a whole lot more turns on the secondary. And if you want to decrease the voltage, like for that pole outside your house, you build a step-down transformer. You do the exact opposite. More turns on the primary and fewer on the secondary. So the crucial point, the whole secret sauce, is what's called the turn ratio. The ratio of turns on the secondary coil compared to the primary coil is what decides the new voltage. It's a direct relationship. If the secondary side has 100 times more turns, the voltage gets stepped up by 100 times. It's that elegant, and it's that simple. Now, as brilliant as this whole design is, no machine is perfect, right? Some energy is always going to be lost in the process. So let's take a quick look at where a transformer isn't perfectly efficient. There are really 2 main culprits for energy loss. First, you've got what are called core or iron losses. This is just waste heat created because the iron core is constantly being magnetized and demagnetized. This happens anytime the transformer is turned on. Then you've got copper losses. This is way simpler. It's just the natural resistance of the copper wires themselves. And these losses get bigger the more power you're trying to pull through it. But here is the truly amazing part. Even with those losses, transformers are one of the most efficient electrical devices humanity has ever created. A typical transformer runs at 95 to 98.5% efficiency. That is just incredible. Almost all the energy that goes in comes right back out the other side. And this leads to a really cool piece of engineering wisdom. If you want to get a transformer running at its absolute peak, most efficient performance, you design it for the exact point where the copper losses equal the iron losses. That is the sweet spot. Okay, so let's bring all this back home. Let's talk about why this simple, static box of metal and wires matters so much. So here are the big things to remember. Transformers are what let us safely change AC voltage up or down. They work using the amazing principle of mutual induction, so no parts have to touch. The secret to how they work is that simple turn ratio. And they are unbelievably efficient machines. At the end of the day, our modern power grids simply could not exist without them, period.
The transformer is just the perfect example of a piece of foundational technology that works so well and so reliably that it's become completely invisible to us. And that leaves us with one final thought. What other pieces of invisible tech are quietly making your world work right this second?